Now the question is how we are going to design it in Verilog. Let me start with a UAT. UAT nothing but unit under test. Unit under test. Sometimes we call it as DUT. DUT is nothing but a design under test. If I am talking with respect to the main body of the program, nothing but a UAT, let me name that module to be AES. Within the AES module, we need to bother about two things. One is with respect to rounds and one is with respect to final round. As said earlier, we will be talking with respect to 10 rounds, leaving your initial rounds. Round from 1 to 9 we call it as a main round, and the last 10 round let me call it as final round. And within the round we know that 4 steps are involved. Majorly, one is your subsystem or subbytes where your Xbox is considered. Second is shift rows. The third step would be mixed columns. And the last step is your going for the next stage, right? So add round key. So within the subbytes, obviously I'll be bothering with respect to ES box. So I need to design S box. I don't think we'll be making any changes with respect to shift row, where we are just trying to rotate with respect to circular shift left operation. And within the mixed columns, we will be bothering with respect to predefined matrix that is going to compute each and every column. So let me name this to be one column matrix. And within this, I need to go for round key generation. Coming to final round, all will be bothering with respect to subbytes, with respect to shift rows, and with respect to add round key, except mixed columns. So I must define subbytes. So obviously that need to be instantiated with respect to SBox again. I must define with respect to shift rows. And finally with respect to the last key, I am again rename it as add round key. Now talking with respect to the ranges of the port list, we must have two inputs. Let me write it as inputs here. One is your plain text and one is your cipher key. As seen, we have taken example with respect to 128 bits. So the range would be 127 down to 0. As well as for cipher key, it will be 127 down to 0. Coming to outputs, we will be having one out with range 128 bit as well as round key, right? Now talking with respect to main round, we must declare the input and the cipher as 128 bit, so 127 down to 0. Along with we need to have a predefined table archon with 32 bit, so 31 down to 0 I'll be taking. Similarly, if I'm talking with respect to output, it must have a out followed by R key of same 128 bit. Obviously that is going to fed as input for this stage. So this is 128 bit, right? Thereby the port list for this sub byte will also 128 bit. Let me consider input 127 down to 0, followed by its output to be 127 down to 0. Similarly, with respect to shift rows, we will be having an input 127 down to 0, followed by output 127 down to 0 again. With respect to S box, we will be bothering from R rows followed by C columns starting from 0 to F, Since I will be representing in terms of hexa, I can define its port list with input 7 down to 0 and output 8 bit as well. And within the one column matrix, I'll be having an input, a constant row, and a final red as output, for which the range will be 32 bit, followed by an output of 8 bit. This would actually be acting as input for your multi-factor. One more file I am taking as multi-factor. You will be able to understand this once we enter into the programming session. With respect to round key generation, we will be having an input of 128 bit. We will be having an ORCon of 32 bit. And we will be having an out of 128 bit again. Likewise, the same port list is being applicable to final round also. So it do have the same port list with respect to S byte, with respect to shift rows, and with respect to add round key. We can able to analyze it better with the help of a test bench. Now how? Let me show you the RTL schematic, how it will be. If this is my UUT, nothing but unit under test, for which one input is plain text, which is of 128 bit, one input is cipher key, which is of again 128 bits, for which one output would be, I am naming it to be out again as 128 bit, followed by counting of rounds, again 128 bit as well. If this is my UUT, these input ports and output ports of the design are the one through which the design interacts with the external world. You can consider to be surrounding blocks. Now we need to build a code around this UUT which makes the use of input and output ports to drive the outputs and verify its functionality. That's what we call it as test bench. A test bench is constructed in such a way that it can be able to generate all the required validated outputs. So I must be able to design a circuitry which needs to interact with an external world in such a way that its ports list must match. Let me name this to be test bench TB. If you observe with respect to this UUT, the output of this UUT will be acting as input to this test bench. So the register which are being declared as output in this UUT will be acting as wire with respect to test bench. Similarly, the output of these test benches will be actually acting as input for this UUT. So the reg which is being declared as output here, which will be actually predefined as wire within the UUT. And we need to design a test bench in such a way that it must be able to accommodate all the 128 bits of data in a multiple combination circuitry. So let's start designing a UUT and a test bench as well.